All right, good morning, good afternoon, good evening, wherever you are, whatever you're doing. I hope you're having a great day. What we're going to be talking about over the next couple of minutes here is what a space figure is, and specifically how to draw a net or how to identify a net. If you can't draw or identify a net, you're probably not going to be able to do what's needed to figure out the surface area of a figure. And if you can't figure out the surface area of the figure, you can't derive the formula for that surface area of the figure correctly. So all of this is linked that we're going to be talking about over the next couple of minutes. So in looking at the first portion, number one, match the correct space figure with the correct net. I think all of you should be able to do that right off the bat. So take a couple seconds here, pause your computer, and go ahead and do that for me. When you're done, come back to me and we will talk about that. First of all, the very first figure there is a cube, or you could say a rectangular prism, but I'll go with a cube because they look like they're all the sides, all the faces are congruent to each other. And so as a result, C corresponds with that. We know that that is going to be matched up with that one. The next one, I would call it a square pyramid. All leads to one point, the vertex right here. And I would say letter D is the net of that square pyramid. The third one, you notice that the bases are the pentagons here. Just going to highlight that. And so it's going to be a pentagonal prism. Again, it's a prism because there are two bases, not just one. So letter B corresponds with that figure. And the last one, obviously, is going to be letter A, which is going to be your triangular prism. Two bases, both triangles, both bases are parallel and congruent to each other. Okay, now, hopefully you were successful at that. Let's look at the second one. We have to be able to identify what type of net that is going to be right there. Now, that net, the two bases are going to be opposite each other. And so I know that this base here, this figure, and this figure, these two shapes aren't directly opposite each other. But if we were to wrap that thing all back together, put it back together, they would be opposite each other. And so as a result, this is actually going to be a triangular prism. Again, with two bases, you have a triangular prism. Now, a lot of students usually complain, I'm not a good drawer. Now, I know that's not true with a lot of you. You're very good drawers, but you want to claim that you're not. And so how do I usually teach how to draw a regular prism when they put it back together? And I think the easiest way is to go ahead and draw one of the bases, and then try to draw a face that is congruent to the one that you just drew, okay? And also try to make these side lengths here, the corresponding side lengths, parallel. The closer you get to parallel, the more they look alike. So from there, you just connect the vertices, and there you go. You have the actual figure drawn back together. Now, let me just clarify something. Since this portion of the back base is in the background, you can't see it, and you can't see this edge either, I'm going to go ahead and show a dotted line here. Something like this. And that's how I would go ahead and draw the prism out on my paper. Okay? So just giving you a heads up, when drawing prisms, draw both bases, connect the vertices, you should be fine. From there, looking at number 3, this is actually the most important part of the entire lesson today, and that's this. I want to be able to draw out this cardboard box, this cereal box, in a way that shows me every single face, and I want to also mark every single face's dimensions so that we know how to figure out the surface area later on down the road. So a lot of times I start with the very front face. Now, I think you can see that that front face starts with the dimensions of 20 by 14. Okay, we've got the height of 20 and the base length of 14. And so I'm just going to label one side as 20 centimeters and make congruency marks there. I'm going to label another side as 14 centimeters and make congruency marks for that one as well. Now from that point, I'm going to go ahead and fold up the top side. So this top side coming up, I'm going to fold down the bottom side, and I'm going to fold out the right side and the left side. The top side has dimensions of it'll be, this is 7 centimeters, and this is 14 centimeters. So make those congruency marks there. Now I'm going to make 3 because this is 7 centimeters here. Okay? The bottom side, since it's a rectangular prism, will be the exact same. Okay? The right side has dimensions 7 by 20. This length is 20 here. And so it's very important that when you go ahead and draw your net, that you understand that this side length and this side length, because they correspond to each other, they will be matched up against each other, have to be the exact same length, as will these two sides. Okay? For this one, okay. Again, it's got the exact same dimensions as its opposite face. And then from there, the back side. Now the back side has the same dimensions as the front side. And it really doesn't matter where you put the back side. You can put it down below, off to the right, up above, off to the left. I'm going to put it off to the right. Okay, and I'm going to go ahead and say it's a 20 by 14 rectangle, just like the front side is. Okay. Now, is that the only way to be able to draw the net of that rectangular prism? Absolutely not. There's lots of different ways. In fact, we'll talk about more of those ways come Monday or come the next class period. But that is about as basic as we come when it comes to drawing nets. Our next class period, we're going to be looking at some shapes called composite figures, and they will be completely different, and it's going to challenge your ability to unwrap the figure and draw the net. But again, what are we trying to do? We're trying to work our way towards finding the surface area of the figure so we can derive that formula. All right, now, if we go to the back side, I think it would be good for you to go ahead and pause your computer and ask yourself real quickly, choose the net, actually it should say nets, there's more than one, choose the nets that will fold to form a cube, okay? So of the 4 up there, take a moment, see if you can figure it out. When you come back, I'll give you some suggestions as to what you could do here. So go ahead and pause your computer. All right, now I think the easiest thing probably to do, and I did that if you were in my class today, is to go ahead and blow up those nets, cut them out, and then fold them together. That's obviously the easiest. But if this is on an OGT or an ACT, you're not going to have time to do that. You just have to be able to identify and go. And so if you want to take a screenshot of that, throw it into your paint tool, and then go ahead and blow it up and print it off and cut it out. That's a lot of work. But for those of you that can visualize it correctly as of right now, don't worry about this next technique. But if you can't visualize it correctly, let me give you some suggestions here. What you could do is make one of the faces one of the sides of the cube. So in this case, I could make that the front face. Now, if that were the front face, and I was to fold everything back from there, that would make this the top side face, the bottom side face, the right side face, the left side face, and the back side face. Okay? You got to imagine this all coming together. And so this one, that makes a net. That's good. Okay? We like that one. Now for number 2, if I was to go ahead and do something like this, this would be, I'll make this on the front. It doesn't matter which one you make the front, but you build out from there. This would be the top, and that means that this one will come around to be the back side face. This would be the right side and the left side. Now where would this one go? Well, that one would go around to the back side face as well as it continues to wrap around, therefore leaving open the bottom. If that's the case, this one does not form the cube like we'd like it to. Okay? For letter C, if I go ahead and make this one my front side face, that makes this one the top and the bottom, okay, as they fold around. This one folds up to become the left side face. This one goes to the back side. Okay, it folds up and under and then over the back, and that would make this the right side face. So this one does form the cube that we were looking for. Okay, and then if we go to the last one, if this is the front, that makes this the right and the left. This will be the top. As that folds around, this will become the back side face. and this will be the bottom side face. So again, letter D is the answer we're looking for there. So A, C, and D are all options that you could put down. In fact, you should have all of them down to figure that out. So number 5 might be a little more challenging. It's not as, I don't know, it's just, I've just seen students struggle with this one a little more. So see if you can choose all the ones that will become the net within number 5. Take a moment and go ahead and pause your computer and do that. All right, now, which ones should end up being the net? If you did it correctly, it's going to be B and C, okay? And how I chose to do this, if you can't visually do it, and again, if you can't physically print that out, cut it out, and put it all together, what I did was I made this the bottom side for all my bottom side. Okay? Now, if that's the bottom side in each of those, let's say that this is this one right here ends up being the front side face. So the top one is going to be the front side face. Okay? That would make this the back side face for each of these. Back, back, and back. Okay? And then if you have one on the left side, obviously left, and this one's the right. So what are we missing here? For this one right here in letter A, as this folds back to be the front side face, that folds down to be the right side face. So it'll come down in here. This one will fold back to become the back side face, and then this one will fold down to be the right side face as well. We're missing the left side face, which is why that one will not work out. Okay? For letter B, as this folds back to be the back side face, this will be the left and the right side face. So we have all 5 sides that we need. That one's good. The right, as it goes back to be the right, then this will end up becoming the back side face, which is why we have C circled. Okay. Now, as this folds back, I think there's another one. Yeah, over here we can see that this is the left side face. So this is left side. Okay. And then from there, as it continues to fold around, this ends up being the front side face, which is why D is not an option there. Okay? And so that's how you would do those, 4 and 5. For some of you, you'll have no problem with those. For others, you aren't quite as visual, might struggle with that a little bit. For number 6, we want to figure out the number of faces, vertices, and edges that are formed from these figures. Now, a hexagonal, that'd be a 6-sided prism. Okay, the hexagon has 6 sides. And so the number of faces, and again, you may want to pause your computer and go ahead and fill those in. Number of faces, if the base face has 6 sides and the other base face has 6 sides, that means we have 2 faces, each basis. Prism has 2 faces. And then there are 6 lateral faces that connect those 2 bases. So we end up having a total of 8 total faces. Vertices, there are 6 on the one base. There are 6 vertices on the one base, and there are 6 vertices on the other base. So there's a total of 12 vertices overall. Okay? And the number of edges, there are 6 edges on the bottom base, 6 edges on the top base, and there are 6 lateral edges that connect the 2 bases. So there's a total of 18 edges within the hexagonal prism. Okay? Now, for the next one, number 7, the octagonal pyramid, we have 8 sides for the base, which is the octagon. And again, remember, it's a pyramid, so there's just one base here. So we have an octagon on the bottom, and then we have 8 lateral faces leading up to a vertex. So there's a total of 9 faces in an octagonal pyramid. Okay? Number of vertices, we have 8 vertices on the bottom for that octagon and 1 top vertice of the pyramid. And so there's a total of 9 vertices in a pyramid. Now, in a pyramid, what you see here will hold true for all pyramids. The same number of faces equals the same number of vertices. Okay? And so you have to have both be the same. For edges, the bottom base, the octagon has 8 edges, and each lateral face has 1 edge. And so you lead that edge up to the vertex. That would be 16 total edges, okay? Give me 1 second here, I got someone at the door. All right, sorry about that little delay there. So, and so we have that, 9 faces, 9 vertices, 16 edges. And again, if you go ahead and look one up on the internet, you probably can see it a little bit better, and maybe I should have done that for this since I can't visually show you what I'm talking about. Now, there is actually something we can conclude from this right here, the information that we're given up here. There's a link that connects faces, vertices, and edges. And so let's write this up above. This guy named Leonard Euler came up with this formula called Euler's formula. Okay? Euler's formula starts out like this. If we go ahead and take the number of faces and add in the number of vertices, that will equal the number of edges. Now look over there and do the math for me real quick. 8 plus 12 is 20. 18 plus what would equal 20? Well, that would be 2. Let's see if that remains true for the next one. 9 plus 9 is 18. 16 plus what equals 18? 16 plus 2. So you may want to go ahead and memorize this formula right here. Euler's formula. It's a simple formula that connects the relationship of those three together. Interesting, but not earth-shattering. So you can just keep that in mind. So if we apply that formula down here, faces plus vertices equals edges plus 2. Faces is 5. Vertices is 5. And the edges are unknown. Now we can just use algebra to solve. So we would have 10 equals edges plus 2. And if we subtract 2 from both sides to get the number of edges, there would be 8 edges there. Okay? Now, something you might want to think about as a type of bonus problem is this. Give me a second here. I got another break I have to. Okay. So I was just commenting on how I could take this question and make it into a bonus, and here's what I'm thinking. Given the number of faces, vertices, and edges, can you determine what type of shape this is going to be? Okay. Now, the first thing I see is this. Both the faces and vertices are the same number, so I know it's got to be a pyramid. So that definitely gives me a leg up on what I need to do here. So pyramid. Okay. And the fact that there are 5 faces, that means that one of them is the base and 4 others lead up to a vertex. So I'm thinking square pyramid. Now let me think here for a second. If it's a square pyramid, are there 4 bottom edges and 4 edges leading up to the vertex? And that is true. So I would go ahead and put something like this. Square pyramid. Excuse me. Now for the next one, number 9, the faces are unknown. The vertices are 6. And that will equal the number of edges, which ends up being 9 plus 2. Okay? So if we go ahead and solve this, faces plus 6 equals 11. And then from there, subtracting 6, you get the number of faces to be 5. So as I plug that in, one thing I know is definitely not going to be a pyramid. So as a result, I'm going to put a prism down. Okay. Now if there are 5 faces and I know it's got to be a prism, that means that I have 2 faces already that are bases and 3 lateral faces. So if that's the case, with 3 lateral faces, there's 3 sides to my base. That means it's a triangle. So I'm thinking triangular prism. Now let's double check this. Does a triangular prism have 9 edges? There's 3 on the bottom, 3 connecting lateral edges, and then 3 on the other base. So that would be 9. Does it have 6 vertices? Well, you got 3 on the base and 3 on the other base. So that's right. So this is a triangular prism. Okay. Number 10, we have faces, edges, and vertices. So number of faces are 8. Vertices are unknown. Edges is 18. Okay. From there, if we go ahead and solve for edges, we subtract 8 from both sides, we get 12. Okay. And so from there, I see that this is not a pyramid. It is a prism. Okay. And if I go ahead and look, number of faces are 8. 2 of them have to be bases, so that means there are 6 lateral faces. If my base has to have 6 sides, that's a hexagon. So I'm thinking hexagonal prism. Now, does a hexagonal prism have 18 edges? Well, if we think about it, the base hexagon has 6, the other base hexagon has 6, and there should be 6 connecting edges as well, which would make 18. So this is a hexagonal prism. Now, if you notice, those are the same numbers that we came up with in number 6. Okay, so that kind of validates that, yes, it is a hexagonal prism. So, with that being said, there is a homework assignment that is due for our next class period, so I'd like you to go ahead and work on that. You can find that online. And if you have any questions, please come and let me know. Hopefully this was self-explanatory, and we'll go from there. So, have a great evening, and I will talk to you later. Good night.